Hello, everybody. Today we're going to do a little lesson. We're going to talk about the Earth's motion, its rotation, the cause of the seasons, rotation, revolution, and then the moon as the moon goes around the Earth, the different phases of the moon, and then eclipses. So I'm going to do some drawings. I'm going to do a 3D model for you, and here we go. As the Earth goes around the sun, the North Pole always kind of points in the same direction, you could say, because you could think of it this way. If we were to take this whole thing and shrink it down super tiny, and realize that that's kind of in the perspective of the universe. That's what's going on. So super tiny. The North Pole is always pointing towards the North Star. So if this is the North Star Polaris, it's so far away that even as the Earth moves around the sun, it's always pointing, the North Pole is always pointing towards that place. So Polaris doesn't change its location in the night sky as the Earth goes around the sun. Okay, so let's go back to our model. As the Earth goes around the sun, the North Pole is always pointing in that same direction, always still pointing towards Polaris. Okay, and so this is the revolution of the Earth. Here's a three-dimensional model where I have a globe that's spinning to show day and night, and the basketball in the middle is supposed to be the sun. And you can see the Earth spins and it maintains that tilt as it goes around the sun. When it's in this position, you can see the North Pole is kind of pointed towards the sun. What that means is that the sun's rays are hitting the the northern hemisphere more directly than the southern hemisphere. The days are longer in the northern hemisphere. The sun's rays are hitting more directly. And so that's the cause of our summertime. When, however, uh, the Earth is on the other side, and so when the North Pole is pointed most directly towards the sun, when it's pointing most towards the sun, that's what we call the summer solstice for us. And that's usually around June 21st or so. When the Earth is on the other side, then you can see that the sun's rays are hitting the southern hemisphere most directly. And this is our winter. So when the North Pole is pointed away from the sun, this usually happens around December 21st. And that's what we call our winter solstice. And then when it's what you could say sort of directly across from the sun, so this is when the sun's rays would be making a 90-degree angle with the axis, with the Earth's axis. This is what we call the equinox. And we have two equinoxes, one in the spring and one in the fall. So around March 21st and then also around September 21st. And equinox means equal night, equal, and nox, right? Latin means night. So it's equal day, equal night, 12 hours for both the northern and the southern hemispheres. It's this tilt of the axis. This is what's the cause of summertime and wintertime. It's the cause of the seasons. We are actually a little bit closer to the sun during January, right? During our winter is when we're actually a little bit closer to the sun. Most people think that the summer and winter are caused by Earth being closer to and farther from the sun. And the Earth does get a little bit closer and a little bit farther from the sun, but that's not the cause of the seasons. The cause of the seasons is this tilt of the Earth's axis and how direct the sunlight is and how long the days are. So there's a little tutorial in the Earth's orbit. And keep in mind too, what's causing day and night is that the Earth is spinning. So the Earth is spinning, it's rotating around its axis, and it's revolving around the sun. And because of the tilt of the axis, that's what causes the seasons. Also, as the Earth is going around the sun and spinning, the moon is also going around the Earth. And I've tried to depict that here. And the moon's orbit is sort of tilted with the Earth's axis, like this. And so sometimes it's on this side, sometimes it's on this side. And this takes 28 days, roughly 28 days for it to go around one time. Here's a 3D model. So I've got a little ball to go around the Earth, showing what the moon is doing. And then on this side, notice here that, so this would be the equinox position. Notice that the moon actually does come and get perfectly lined up with the sun and the earth at various points. So this would be on the other side. This would be our winter. You can see the orbit of the moon takes it kind of above and below the line of the earth and the sun. And then here's the other equinox. Okay. And as you can see, like in this position, we would be looking at the moon from here, right? We'd be looking at it that way. And the side that we're seeing, that's the side that would be lit up because the sun's rays are hitting that side directly. So this whole side would be lit up to us. And what we would see then, our view of the moon would be something like this. Right? We'd be looking at it directly from the side, and the side that's facing the sun would be lit up. And that means only half of it would look lit up to us because we'd be seeing, the side where the sun is, and then the other side would be dark. So this is a quarter moon, either the first or last quarter moon. Let me get rid of some of these things now. If we go over to this side, when the sun is in this position relative to the moon, the sun would be hitting the other side of the moon, and so we wouldn't see anything. The side of the moon that we would be looking at would be totally dark. But then when the moon was in the position, this far position over here, which is a little tough to see, the size of the model is a bit too big for the page. Let me make it a little smaller. When the moon is in this position, then we would be looking at it here, and that whole side would be lit up. And so that's for us is a full moon. So when the moon is in this position here, this is a new moon, and this is a full moon. Now notice that it's tilted, right? That the axis is tilted. What that means then is that when the Earth is at its solstices, right, on either side over here and over here, the moon never gets between the sun and the earth. It's always down or up, or when it's on the side, it's over there. But when the earth is in its equinox positions here and here, that's when the moon can come directly between the sun and the earth. And the earth can come directly between the sun and the moon. And that's the cause of the um, eclipses when we have an eclipse, right? So in order to have an eclipse, we have to have the sun. And let's take a solar eclipse, for example. And then we have the Earth. And then the moon would come directly between them. And so the sun's rays would cast a shadow, and there would be a dark spot on the Earth where the moon's shadow is. For a lunar eclipse, that's where you have the sun and the Earth, and the moon is on the other side. The moon passes into the Earth's shadow and is totally dark. Right? But again, this can only happen when the sun, moon, and Earth are lined up, and that only happens because of the tilt of the moon's orbit when the sun or when the Earth is in its equinox positions here and here. So thanks for watching. I hope that was instructive, and we'll see you soon.